So as we were discussing last time, our goal in this lecture and going forward into a couple of other lectures will be generalizing the notion of sampling theorem in terms of the geometry of vector spaces. And for that, we'll indulge into a little bit of abstract mathematics. And the purpose of that is the power that abstract mathematics gives us is that if we understand the abstract tools well, then it becomes a very simple exercise to take the same set of results and apply them to different settings. Just to give you an example, in your elementary school, I'm sure when you learn addition, subtraction, multiplication, you learned it in an abstract manner. You are told 2 plus 4 equals 6, 4 plus 4 equals 8, 10 divided by 2 equals 5. But at the end of the day, what you do with that is that now you can take the same knowledge, you can now add money, you can add people, you can add weight, you can divide money among people. Right? So the basic abstract notions remain the same, you apply them to different settings. Rather than your elementary school teaching you that if you have 4 people and 4 people, that becomes 8, and then reteaching you, well, if you have 4 kilograms and 4 kilograms, it's 8 kilograms. So we are going to do the same in this class for the case of sampling theorem. And for that, we have to learn a few concepts, just like you learned addition, subtraction, multiplication. We have to learn some new concepts that relate to the field called functional analysis. We won't be that deep, thorough, or rigorous, but we still have to understand what some of the basic terms mean. Okay. So last time, as I was saying, what we want to do is forget about a signal being x of t or x of I comma j, where it's two-dimensional or anything. We will treat signals as part of something called vector space. So what we are going to do right now is figure out what is a formal definition of a vector space. That's what we are going to start with. Okay. So we have vector space definition. So given a collection of objects, which we are going to write as capital V, where these objects can be anything. We are not going to say whether they are signals or they are matrices or they are vectors. They are just any collection. We say that V is a vector space over a real line. Vector spaces can be defined over complex too, but we will stick with the real case in here. If there is a way for us to add objects in V and multiply objects by scalars such that the following axioms hold. So the first thing for vector space is that whatever is the collection of objects you are given, you must have a way of adding them. You must define addition over those objects. you must have a way of multiplying those objects by scalars, but that's not enough. You must have certain additional properties that must be satisfied to make to turn that collection into a vector space. And if those properties are satisfied, then every object within the vector space, we use the term vector for that. Okay? So the first property is that of commutativity, which is that if x plus y should be equal to y plus x for any x and y belonging to V. So something which we know for numbers, for example, that should hold for the objects too. It doesn't matter whether you add one thing to the other or the other thing to the first thing. Okay, you change the order, the answer shouldn't change. The second is again the natural property of associativity, which is that if you are adding three objects, then the order in which you add them shouldn't determine your answer. For x, y, z belonging to the vector space. Again, this property just says that if I first add x plus y and then add it to z, or I add y plus z and then add them to x, the answer shouldn't change. The last property is that of distributivity, which is that if alpha is a scalar, then alpha x plus y is simply equal to alpha x plus alpha y. And if beta is a scalar too, then alpha plus beta x are simply equal to alpha x plus beta x. These are some of the common properties that you are already aware from addition. Those should hold. Now, the next properties are a little bit more abstract, but there is something called an origin in a vector space. In V, the origin is defined by the following fact. We denote it by 0, and if sometimes I have to differentiate between 0 number and 0 vector, then I'll just put this bar under the 0 to signify that it's a vector and not a scalar. Okay, so if I add 0 or the origin to any vector, and of course, since we already believe that there should be commutativity, if I add something to the 0, I get back that same thing. That's the definition of origin, even though that thing may not look like the classical 0 or origin. The definition of a 0 vector is you add it to anything and you get back the same number or same vector. The fifth property of vector space is that there must be a unique additive inverse. So for every x belonging to the vector space, there exists a unique vector which we are going to denote by minus x. It's not a subtraction operator, but rather it is, I'm calling that vector as minus x. Okay? Belonging to the vector space such that the following holds. I add this additive inverse to x, and of course the order doesn't matter, then I get back the origin. And the last property is for every x belonging to V, if I multiply the x with a scalar 1, then I get back the same quantity. I get back the same vector. It's the multiplicative identity. So together, these 6 properties, if any collection of objects satisfy these properties, we call that collection a vector space. And we call every single object within that collection as a vector. Okay? And the properties are very intuitive. All the addition properties that we know, and in addition, it should have an origin, an additive inverse, and a multiplicative identity. Now, examples of this, one is, of course, the classical example that we know, which is just the Euclidean space. So if you think about examples, then we know that Rn, and the collection of n-dimensional, what we traditionally call vectors, is a vector space in the abstract sense. So it is a vector space for any n. We can verify that the origin is a typical 0 vector, 0, 0, 0, 0. We know how to add in Rn vectors, we know how to multiply things, and they all hold. Now, if I define R plus, which is the positive side of the real line, okay? So let's define my R plus to be the positive side of the real line, which is this part. The question is this a vector space? This R plus is not a vector space because additive inverse does not exist in this region. Okay? It's a line segment, it's not a vector space. Now, those are sort of classical examples. Let's talk about something that we traditionally don't think of as vectors. So we have been studying, for example, this space called L2R, which is defined as the collection of all signals which have finite energy. Well, it turns out that this L2R is a vector space. And it is very easy to see why. If we define addition of vectors, now each vector in L2R is a whole function. We are calling functions as vectors. So instead of writing xt, we can say x belongs to L2R and y belongs to L2R. So we have to, first of all, by the definition of vector space, define addition on this space. Well, addition is very simply defined by, we can say x plus y is equal to simply x of t plus y of t. What does it mean to add two functions? You just add them at each value of t. That's the way to add two functions. How do you multiply a function with a scalar? You simply multiply the function value at t with that scalar. And because of the fact that you are defining addition in terms of the canonical addition, it becomes almost trivial that you will end up with, for example, additive inverse. What is the additive inverse of a function x? Just take the same function and put minus in front of x of t for every value of t. What's the origin? Take the function which takes value 0 everywhere. Right? The only tricky thing in this context is verifying. For this to hold, you need to verify that this itself also belongs to L2R, which means that if you add, so vector spaces are closed under addition. They have to be, by definition, closed under addition. It follows from, it's just a consequence of our commutativity property says that x plus y equals to y plus x, and that sum has to belong to the vector space. So what you are saying is, to make this a vector space, you have to argue that if you add two functions which are finite energy, then you get back another function which is also finite energy. This L2R, you have to verify, if you are defining it like this, that if you add two finite energy signals, you get back another finite energy signal. That is not that difficult to show, although we are not going to go into that. Okay. Now, another vector space could be, and that may sound initially very strange to you since we are not used to calling these things. Let's think of space of all n by m matrices. And define addition in terms of the between those matrices as the usual addition that you are taught for matrices, entry-wise addition. Well, because of the fact that, again, we are just using the canonical addition, it turns out that the space of all matrices is a vector space, and you can think of each matrix essentially as a vector, but vector not in the sense of a column vector, a vector in the sense of an abstract vector. Okay? So any collection, as long as it satisfies these 6 properties, it becomes a vector space. So space of all n by m matrices, addition defined in the classical sense is a vector space. Now, we started talking about vector spaces by using the example of Rn, and we said, well, in Rn you can add vectors and you can multiply them by scalars. Let's abstract that notion. So we'll keep that example of Rn in our mind and define further abstract notions. So the next thing we want to understand is the concept of a subspace. Which is essentially a vector space within a vector space. So if you think about, for example, R2, and you might have been exposed to that in your undergraduate, and if you think of this line which passes through the origin in R2, this line is sometimes called a subspace of R2. This line which extends all the way down to all the way up. Okay. Any line which passes through the origin in R2 and keeps on going, it's typically termed as a subspace of R2. Similarly, if you think of a plane in R3, that is also a subspace. Now, what is the formal definition of a subspace? Let's look at that. So the definition is a non-empty subset S of a vector space is a subspace whenever the following two hold. Number one, if X belongs to S and Y belong to S, then this implies that X plus Y must belong to S. So it should be closed under addition. And the second is that if X belongs to S and we have a scalar alpha belonging to the real line, then alpha times X belongs to S. Collectively, you can think of a subspace of a vector space as simply a collection which is closed under addition, which is closed under linear combinations of vectors. Okay? So just as we talked about previously, if this line didn't extend from one end to the other end, then it won't be a subspace because it's not closed under linear combinations. Okay? Similarly, a line which has perhaps a hole in between, it won't be a subspace. So examples will be line in L2, in R2, that will be yes. But if we talk about a line segment in R2, that will be a no, because that is not closed under all linear combinations. You can add 2 points in that line segment and get a point which is outside that line segment. Basic geometry. Okay. Now here is an interesting fact about subspaces, which we are not going to formally prove. A subspace is itself a vector space. What that means is that even though we define the subspace only in terms of that it has to be closed under linear combinations, just using that fact, you can show that a subspace satisfies all the properties of a vector space. Because it's a subset of a vector space, so it carries some of those properties automatically, and if you go through them, it becomes rather trivial. Now, the only thing is the following. We talked about one of the facts of if you want to prove vector space, that a subspace is a vector space, we must show that there is something called an origin in the vector space. Now, in our definition of subspace, we never said that the origin has to belong to it. But just by the fact that it is a subset of the vector space and that it is closed under linear combination, it turns out that the origin, the zero vector, indeed belongs to the subspace. So the only non-trivial fact, especially if you have never done abstract mathematical proofs before, is showing that the vector 0 indeed belongs to the subspace, because if it does not, it cannot be a vector space. Now, to show that the origin belongs to subspace, it is enough to show so we can show that 0, which is a scalar now, I'm not putting the bar down, multiplied with x equal to 0 for x belonging to subspace. Why? Because our definition of subspace says that if we multiply any scalar with our element of subspace, it has to belong to the subspace. So 0 dot x we know belongs to the subspace. We just have to show that 0 times x is the origin. Okay. We know this belongs to the subspace by definition. So if we can show that the equality holds, if this equality holds, now we have to be a little careful with using our usual ways of doing additions or distributions, because we only have to work with the properties that we have defined. We cannot assume anything else. Okay? We have to say that we don't know anything about mathematics other than the properties that we have defined. But if we do that, then essentially we are cheating by using properties that are not part of the definition of the vector space. So the proof may look rather silly to some, but that's the only way you can formally prove it. So the way it will go is we will write 1 dot x, where 1 is scalar, plus 0 dot x. Okay. Now this, by the distributivity property, I can write it as 1 plus 0 x. Okay. And 1 plus 0, since those are scalars, the usual rules of addition apply. 1 plus 0 is 1. So I get equal to 1 dot x. Now by the multiplicative identity, whenever I multiply 1 with a vector, I get x. Okay. So we have shown that 1 dot x plus 0 dot x is equal to x. Now the other fact that we know is that x plus minus x, by the additive inverse property, that has to be equal to the 0 vector. So what I'm going to now do is put this x here. Since I have shown that this x is equal to this quantity, okay, I am going to replace this x with 1 dot x, 1 dot x plus 0 dot x, okay, plus minus x. Now by the associativity property, I can add them, I can change their order. So I'm going to do 0 dot x, and I'm going to take this 1 dot x with the other term, 1 dot x plus minus x. Okay. Now again, I'm going to use the property of multiplicative identity, which is that 1 multiplied by x is simply x, x plus minus x. And now the property of additive inverse, which is that x plus minus x is the 0 vector. So I have 0 dot x plus the 0 vector. Now a 0 vector added to anything gives us back that same thing. So I get 0 dot x. Remember, in this proof, we can't say take this to the right, take this to the left, because we cannot assume those things can take place. We had to work with our elementary definitions. But effectively, what we have shown is that if we multiply any vector by 0, then we get back the 0 vector. And by definition, if we multiply any vector by any scalar, it has to belong to the subspace. So that means the 0 vector belongs to the subspace. Okay, so proving the other facts about subspace being a vector space are trivial, and you can formally then argue that any subspace is itself a vector space. And the other fact is, of course, that 0 belongs to every subspace. If a subspace does not, so think about just if you extend that logic and you say, I have a line in R2, that line cannot be a subspace until it passes through the origin. Okay? Otherwise, it's technically not a subspace. So this is sort of just showing you, giving you a little bit of familiarity with the abstract mathematical proofs. You can go home and think about it a little bit more, but we are not going to do any more proof about this, about subspaces. So let's look at, though, other than lines and planes, what can be a subspace? Okay. So we'll go back to our earlier example, and we'll relate to what we have been studying. So we have been studying about L2R, and we argued that that's a vector space. We also, in our sampling theorem, talked about the space of band-limited signals. So we said that this band-limited omega n, L2R, this is, of course, a subset of L2R. It's all those finite energy signals which are band-limited. That's the definition of band-limited, the space of band-limited signals. Now, you can verify that this space of band-limited signals is a subspace. What do we need to prove that it's a subspace? We need, of course, that it has to be a subset, that is given. And secondly, it has to be closed under linear combinations. Okay? And that is trivial to show. What you have to show is that if you take one band-limited signal, you take another band-limited signal, you add them and perhaps scale them by some scalar, you get back another band-limited signal. If you can show that, then you have shown that it's a subspace. So the proof is rather trivial, and we'll leave it for an exercise, or perhaps an assignment. Okay? So this will be shown in an assignment. Okay. So we are slowly building something that looks very similar to the usual vectors that we do. So what is the other thing that we care about in vectors? We like to measure their lengths. If you are in R2, for example, and you are given a point, which is essentially a vector, you would like to know the length of this vector. So if I define a vector v, which is v1 and v2, we can measure its length. What's an equivalent notion in a vector space? That notion of length is called a norm. And intuitively, what the norm does is it tells us the size of a vector. It tells us whether something is large or small. For example, you may want to talk about this function is perhaps has a longer length. It has a bigger norm. Okay. We know how to define norms in Euclidean spaces. For example, if you are in R2, the notation for norm is these two double bars. In R2, we sometimes use this. And we define the norm to be simply v1 square plus v2 square. If you are in more than 2 dimensions, you just extend that. So we have all seen how to take lengths in Rn But what does it mean for something to be a length in a general vector space? That is called a norm, and a norm is simply, I give you a vector, you tell me that's its length, so it's a function, it's a mapping, but it has to satisfy certain properties. For example, one trivial property that comes to your mind is that length cannot be negative. You don't want to say this vector is of length -10. So these kinds of properties, which are sort of trivial in Rn, we want to give them a formal definition. Okay? So the formal definition of a norm is that a norm on a vector space is a function which we write by these two double bars, which has domain being the vector space and range being the real line, such that the following hold. Number one is the positive aspect of the length. Norm of any vector has to be greater than or equal to 0. It doesn't make sense to talk about length in negative terms. Okay? And the second thing is that the only thing whose length should be 0 should be the 0 vector. It doesn't make sense for a vector which is not an origin to have 0 length. So x is greater than or equal to 0, and x can only be equal to 0 if and only if this x is actually the 0 vector. The other thing is the scaling. So if you take a vector in Rn and you multiply it by a scalar, let's say 2, what happens? It expands the length of that vector. Okay? So a similar property should hold, which is that if I multiply my vector by a scalar, then the length of that new vector should simply be the absolute value of my scalar times the length of my old vector for alpha in the real line. And the third property, which is again very intuitive in R2, so let's say you have these three vectors in R2, v1, v2, and v3. There is something I'm sure you guys have seen many times, which is that the length of v1 plus v2 has to be less than or equal to the length of v1 plus v2. It's called the triangle inequality. So triangle inequality in Rn makes absolute sense. And if you want to define something to be a length of a vector in vector space, you want a similar property to hold. So the third property is that x plus y, the triangle is less than or equal to x plus y. Okay? And this property is called triangle inequality. And any vector space that has a norm associated with it is called a normed vector space. So it turns out that in for example, R2, the usual length that you measure is not the only norm. You can measure norm in many ways. So examples, in R2, another norm could be defined as, and it is written as with a 1, that is defined as x1 absolute value plus x2 absolute value. And you can verify that that is indeed a norm. Another norm that is defined is termed as the infinity norm, which is simply the max of x1 absolute value, x1 where x1 and x2 are just the components of the vector. So I'm writing my vector in R2 as this. And similarly, you can extend these definitions of norms to other cases. But let's go back to the case of functions. What is the definition of a norm in the space of finite energy signals? So what is a norm in L2R? And the norm in L2R is defined as the following. The notation that is used is L2, and it is simply defined as minus infinity to infinity. You measure the energy squared dt, and then you take the square root. Okay? That's the definition of a norm. You are essentially measuring the length of vectors in L2 by looking at what is their energy, square root of their energy. Okay? Now be careful that if I actually erase this 1 over 2, the square root, then this thing is no longer the norm. Okay? This actually, if I remove the square root, then I don't have the triangle inequality. So this square root is critical for me to have the triangle inequality. Okay? We are not going to go into the verifying that this is indeed a norm, but that is how I will define norms on functions. Okay? Now, we are just going through similarities, and the next thing then we need to do about is we have gone through the notion of additions, subspaces, how to measure lengths. In Euclidean geometry, the other thing we are interested in is measuring angles between vectors. For example, if in R2, if I am given this vector v1 and this vector v2, right, then if this angle is 90 degrees, we say that v1 is orthogonal to v2. We write this often as v1 orthogonal to v2. Or there could be other angles involved between the vectors. If the angle between two vectors is 0, then we say they are, apart from a linear scaling, they are exactly the same vectors. They are pointing in the same direction. So telling us that if we can figure out what is the angle between vectors, we can say how similar or dissimilar two vectors are from each other. A vector in R2, which is like this, v1, and a vector in R2, which is like this, v2, if they are in the same direction, which means their angle is 0, whatever I can do with v1, I can do with v2. I can scale them and move them around. They are effectively, apart from the fact that their length might be different, they are effectively the same thing. On the other hand, if I have a vector which is like this, let's call this v3. Now this vector is completely different from these other two. Why? Because the angle between them is almost 90 degrees. So in Euclidean space, we have a very good sense of how to measure angles. And in the Euclidean space, we call this sometimes in terms of inner product. For example, if I am given a vector v in Rn, v1 and v2 in Rn, okay, the inner product between them is defined as v1 transpose v2. Okay. And if this ends up being 0, we say that the vectors are orthogonal to each other. On the other hand, so this is one example. If the other hand, if we have that both the vectors have length 1, and we find that v1 transpose v2 equals 1, then it turns out that they are collinear. The only time it can happen is if both the vectors point in the same direction. Okay. So what we want to do is take this notion in Euclidean or Rn spaces and abstract it into a more general notion. In particular, we want to define something called inner product on a vector space. So what we want to do is define inner product on an arbitrary vector space V and the usual notation for that is you have two angular brackets. For example, in Euclidean space, I can take this V1 transpose V2 and I can write that as V1, V2, V1. Put angular brackets in. Okay, that's another way of writing the inner product. So an inner product is just, it takes two arguments, it takes two vectors, whereas a norm takes one vector, an inner product takes two vectors, and then it maps it onto the real line also. But unlike the norm, it has different properties. So the definition is an inner product is defined on the Cartesian product of our vector space and maps onto the real line or complex line, depending upon whether we are talking about real scalars or complex scalars. So there are four main properties. Number one is that if I have three vectors and I take the inner product of x plus y with z, then the inner product is linear in the first. It's linear in the first argument, which means that I should be able to write it as inner product between x and z plus y and z. Example of that, of course, will be if I think about I have three vectors in Rn, R2, X belonging to R2, and Y also belongs to R2 and Z. Then I have X plus Y. Okay. Inner product of this should be equal to X, Y plus XZ plus Z, XZ plus YZ. Okay. And indeed, that is the case. You can verify that Z transpose X plus Y. We know from our linear algebra that is simply equal to Z transpose X plus Z transpose Y. The other property is that of multiplication with a scalar. So if I multiply a vector with a scalar and I take the inner product, if the multiplication happens in the first argument, then I can simply take out the scalar. That is equal to alpha times X and Y. Okay? So I can do the inner product and then multiply it by a scalar rather than multiplying with the scalar first and then taking the inner product. Again, you can see that that's trivial in the R2 or Rn case. The third property is that if I change the order of inner product, then the answer that is simply given by conjugation of the original inner product. Now, of course, if this inner product is defined over reals, then whether you have conjugation or not, it's not going to change anything. In which case, it says that if you change the order of inner products, the answer doesn't change. So whether we do X transpose Z or we do Z transpose X, I'm sure you all know that that is the same. And the final property is that if I take the inner product of a vector with itself, then it has to be greater than or equal to 0. It cannot be negative. And it is equal to 0 if and only if X is itself a 0 vector. Okay. And any vector space which has an inner product defined on it, it's called a vector space with an inner product can be turned into a normed vector space. How basically you can define the norm of X to be simply equal to the inner product of X with itself square root. Okay, so every inner product helps you define a norm. And the classical example, of course, is that if I do X transpose X in R2, that is simply equal to X norm squared. Okay? Because this is equal to simply I equal to 1 to, well, we are doing R2, so that is xi squared. Okay? So if I take the square root, I get if I take the square root of the inner product, then I get the square root of this, I get the square root of this, and I get back to this definition. Okay. So in Euclidean space, the norm is actually defined through an inner product. If I just give you a vector space with an inner product, you automatically get a vector space with a norm. Now, the reason we want to do inner product is because we want to understand angles between abstract things, abstract objects in vector spaces. So this is where it becomes handy. Take the example of L2R. Now this we have so far argued it's a vector space, but what does it mean to say that one signal is similar to another signal? Or to say that one signal is orthogonal to another signal? I'm sure in your undergraduates you have done many exercises where question comes, show that this collection of signals are orthogonal, and then they say, i.e. show that if you do this operation, the answer is 0. This is sort of a formal way for us to saying when are two signals orthogonal? When are two signals very similar to each other? So if we can define a notion of inner product on this space, on the space of finite energy signals, I can give you two signals and you can tell me these two signals are similar to each other based upon their inner product, or they are completely dissimilar because their inner product is 0. So what's the definition of inner product on L2? The definition of inner product on L2R is given x, y, we simply multiply pointwise the two functions. The second one, we take the conjugate transpose, we take its conjugate, we do dt. That's the way to define inner product in L2R. Now we can define orthogonal signals. Or even similar signals. So you give me two signals, I simply compute their inner product, x of t, y conjugate of t, dt, which I'm defining to be the inner product. If this is equal to 0, then we say, just like in the Euclidean space, we say that the signals are orthogonal to each other as if the signals were vectors, and in reality they are vectors, but in an abstract sense. But if you want to sort of conjure up the image of Rn, you can think of these vectors as your usual vectors, and the angle between those two vectors is 90 degrees. So these signals are orthogonal, which means they are maximally dissimilar. And similarly, you can define inner products on other spaces. We won't go into that, but you can define, for example, inner products on space of matrices. And then you can say a matrix is orthogonal to another matrix based upon that inner product. That's an abstract notion. That's not what we are going to cover in this class. Because for us right now, the emphasis is L2R. Okay. Now, the final pieces that we need to cover which we won't be giving rigorous definitions. The definitions that are going to come next are, just want to warn you, are not fully rigorous. So if you are interested, you will have to go and read other resources. But I just want to relate them to what you have seen in your linear algebra classes, for example. And those things are concepts of basis, dimensions, and projection onto an orthonormal basis. All of you have seen in your linear algebra similar notions for vectors in Rn. We are going to sort of generalize them to the notion of vector spaces without too much rigor. And the rigor that is going to be lacking here is due to the fact that we might be dealing with an infinite amount of signals or vectors, and that makes things a little tricky, because we have to talk about things like convergence, and I'm sure none of us are ready for that. So, but just to briefly give you some sense and remind you from your linear algebra, if we have an n-dimensional Euclidean space and I take n vectors in that, then those collection of vectors, we call them a basis if two things happen. Either one of those two things are equivalent to each other. Number one is every vector in Rn can be represented uniquely, and that is the key. It has to be uniquely by a linear combination of v1 up to vn. Which means that if you are given a vector v, you can simply write that as alpha 1 v1 plus alpha 2 v2 plus alpha n vn. And further, there is no other alpha 1, alpha 2, alpha n that will satisfy this property. So it is a unique collection of scalars. Okay. If a collection of vectors satisfies that, then we call those vectors basis in Rn. Okay. Another definition which some of you might have seen, or which more of you might have seen, is v1 up to vn is a basis for Rn if this collection is linearly independent. If they are linearly independent, which means that no vector can be represented as a linear combination of any other vectors in that set. Which means that vi for any I cannot be represented as a linear combination of v1, v2 up to vi minus 1, vi plus 1, and vn. Effectively, if you take all the other vectors in the set except itself, you cannot write it as a linear combination of those vectors. And when you have a basis, the dimension in Rn is defined as the number of vectors in the basis of Rn is called its dimension. This is a unique number, and of course we know that in Rn the number of basis elements you need is n, so Rn is an n-dimensional space. That's the term we use. In a sense, dimension gives us a clue about how big something is, how big a collection of objects is. So like R2 is smaller than R3 in some sense. And the bigger n is, the bigger the dimension is, in some sense, the bigger that collection is. Okay. And similarly, there is a third thing we can do in Rn, which is that of projection. But before that, let me just an example of bases. Of course, if I take in R2, the bases are the canonical vectors. v1 equals 1, 0, and v2 equals 0, 1 are basis for R2. They are called canonical bases. Of course, every vector v equal to v1, and let's write it alpha 1 and alpha 2. I can simply write that as alpha 1 times 1, 0 plus alpha 2 times 0, 1, which is alpha 1 v1 plus alpha 2 v2. So basis helps us write a vector in terms of its components. Now the last thing we often do in Euclidean spaces is projection onto a subspace. So if you are given, let's say you are given this subspace, so this is a subspace in R2, and you are given a vector here v. There is a notion of projection onto this line. What is the definition of projection? The closest point to this vector which lies on that line. That is defined as the projection. Okay? And the way we do that is we draw a 90-degree perpendicular, and this thing is called v hat, the projection onto the subspace. Okay? If you guys, I'm sure, remind yourself from undergraduate physics or maybe high school physics, where you have force and you're trying to decompose it into x and y coordinates, that's exactly similar. I've just tilted the subspace. So in Euclidean space, you can approximate vectors by closest points on subspaces. How you can do that? You simply drop a perpendicular onto that, and you say wherever that perpendicular hits, that is your approximation. Okay. Now, there is also a closed form expression for this projection, which you may or may not have seen in your undergraduate linear algebra. If you have not seen, just take it as a fact. Okay? Because most of it, what we want to do is, once we introduce these facts, we are going to use them as known things. If you are interested, you should spend time reading these things up on Wikipedia or a good linear algebra text. But for the purpose of this class, if at the very least you can remember those expressions, that is all we will need for the most time. So if you are in Rn, or in this case R2, there is a way for us to compute this projection. And the way to compute that projection is, the best way is use an orthogonal basis of your subspace. So since a subspace is a vector space in Rn, it has basis the way to project onto a subspace, actually let's change this Rn to Rn just to make it more general. So let's say you have a subspace in Rn and it has basis. Denote that subspace by S. Now typically, not always, typically you are working with subspaces which have lower dimension than the dimension of your bigger vector space. So denote that subspace by S, and let's say that dimension of S equals to M, which is less than N. Which means that every vector in that subspace can be written as a linear combination of M vectors, which are the basis of that subspace. Now, what we will need is, we will not be working with arbitrary basis, we will be working with orthonormal basis most of the times. So orthonormal basis is the collection which has this additional property that they are all orthogonal to each other and their length is 1. That's the definition of an orthonormal basis. So it has an orthonormal basis B1, B2 up to Bm, and they are orthonormal. This means that Bi and Bj, the inner product, is equal to 0 for all I not j. Okay, and since we are in Rn, simply we can define that as the transpose Bi Bj. And the other thing is that Bi equal to 1 for all I. And again, since we are in Rn, that is this, and that means Bi transpose Bi square root equals to 1. Okay? If you have a subspace in Rn and someone comes and gives you its basis vectors, and someone comes and says, here is another vector in the vector space, find the closest point on that subspace, which is found by dropping a perpendicular. The closed form expression for that in this case is simply then a vector V in Rn can be approximated by a point on on S, as you write it as V hat, and the way it is computed is You take your vector, the vector that you want to approximate, you compute its inner products with all the basis vectors. You compute its inner products with all the basis vectors, bi, and when you compute that inner product, you multiply that inner product with the basis vector itself, and you sum all of them up. I equal to 1 to m. Okay. Now in the case of Rn, you can of course write that as bi transpose v times bi, which is simply b times b transpose v, where this b is defined as b1. It's a matrix containing all the vectors in the basis. Okay. But the key point is, whether you understand how it comes about, whether you have seen in your linear algebra at the undergraduate level, the key point is this approximation, at least in Rn. If I give you a basis in Rn for a subspace and that basis is orthogonal, and I say draw a perpendicular from any point onto that subspace, which is essentially the closest point of that vector v on that subspace, the formula is simply given by take inner products of your vector with the basis vectors and then multiply with the basis vectors and add them all up. This operation is called projection. In finite dimensional, it is very well defined, nothing to sort of extend. In vector spaces, in general vector spaces, we have similar notions. We have notions of basis, we have notions of dimension, and we have notions of projection. The only difference is that in an abstract vector space, the number of basis elements that you need can be infinite. You can have infinite dimensional vector spaces. What does infinite dimensional means? You need to have an infinite number of vectors adding up with each other to give you any point in that vector space. So we will remind ourselves of this very fact in the next class, and this is where we are going to stop with the abstract notions. In the next class, we will remind ourselves and then think about the fact that we have already said L2R is a vector space, that the space of band-limited signals is a subspace of that vector space. And then we'll see that sampling is nothing but the very formula that last time we wrote after sync interpolation. We'll look at it again and realize that sampling is nothing in the Shannon-Nyquist setting but projection of any signal onto the subspace of band-limited signals, where the projection is given by exactly the same formula. But now instead of our Euclidean vectors, we have vectors which are essentially functions. And if we learn that trick, then we'll see that we can change the kind of space we are working with, change band-limited signals to something else. And the general principle will remain the same. And the same trick you can apply again and again to different classes of signals. As long as the class of signals you are dealing with is a subspace of L2, and you have orthonormal basis, just take the inner products of your signal, multiply it with your basis elements, and you have a sampling theorem. And we can derive many sampling theorems like that. But we'll pick up from here in the next class.